So I know that we've been really struggling with the idea of momentum and inertia since I haven't really taught you guys those terms yet because I was waiting to teach them later, but I think we need to go ahead and talk about them. So first let's talk about inertia. Inertia is the resistance that an object has to an acceleration, to a change in its motion. Basically, it's how much it can resist a force being applied to it. And that value is proportional to its mass. So the heavier something is, the more it can resist being pushed. So if I've got a little cart, by itself, it can't really resist that much because it's pretty lightweight. But then as I start adding more masses to it, it gets heavier and heavier. And once it gets more heavy, it takes a little bit more force to get it going. So heavier and heavier objects have more inertia. And then momentum is something else that we've been a little confused about. When we were doing the example problems with an object slowing down, so with Colonel Stapp on the rocket sled, he's slowing down because of the rockets that were decelerating him, or in the problem where you had the drag race car, and that was slowing down because of parachutes. The parachutes were causing him to slow down. You guys were really wanting to have there be an applied force pushing it forward. And what you were thinking of is its momentum, and a lot of you even used that term to describe the fact that the object has momentum going forward, which is awesome. That is true. There is momentum, but momentum and force are two different things. So an object's momentum is its mass times its velocity, the product of mass and velocity. So here's my momentum equation. The symbol for momentum is actually P because M is already being used for mass, and it comes from a Latin word for momentum, which is, I can't remember what it is off the top of my head. I should have looked that up before this, but that's okay. But there's a Latin word for momentum that starts with the letter P. That's where it comes from. And so it's mass times velocity. The units for it are kilograms times meters per second because mass is in kilograms, velocity is meters per second. And you would think that considering the units for force being kilograms times meters per second squared, that they would have come up with a great name for that, like newtons, but they haven't. So you actually do write out kilograms times meters per second squared. In a future lesson, I'm going to show you that there's actually another unit that you can use for it that's a little bit shorter, but not that much shorter. I think that we should petition to have the unit for momentum change to be bovies, and it could be a symbol B. No, I'm kidding. Please don't put that unit on your homework or I will count it wrong. Okay. Anyway, but that's what momentum is. It's not a force. It is the object, how heavy it is, times its velocity. And where I think the misconception comes from is the more momentum an object has, the more it could actually hurt another object, like if it were to crash. So for example, let me try these little guys. I'm going to use the magnet-magnet side so that they don't bonk into each other, so these won't actually touch. Okay. So if I just have this little guy here, my little blue guy here, and I have my little red guy here, they're the same mass. If I try to bonk this little guy, we can see its momentum just transfers. It's exactly the same mass, exactly the same. It gets the exact same velocity. It just transfers perfectly to it, okay? Now, let me try adding on some extra mass to this red guy. So now, this guy's going to have a bigger momentum. If I give it the same starting velocity, it has more mass, so it's going to have more momentum, and it's going to be able to accelerate this guy extra. See how much faster the blue guy went there? Let me show you one more time. Yeah, it goes a lot faster there. And if I do the reverse, if I make my blue guy heavy, and I make my red guy not so heavy, this barely even goes. In fact, this thing's strong enough to make this guy bounce back off. And so I think when you guys are drawing free body diagrams, and you're wanting to draw, let's say, the free body diagram of my red object, when it's hitting my blue object, you know that that car can apply a force to my blue object. And so you're wanting to say that that force is like this, that's coming, going forward on that object. But that force is not acting on my red car. My red car can apply that force to another object. And that is where we're going to be getting into Newton's third law. So if you look at the next clip, that's going to be about Newton's third law and how that one works, okay? So this, the free body diagram, if we're looking at my red car, of course, initially I had to give it a little push. And so when I was giving it a little push, there was my applied force on it. But after that, after I released it, there's no more forward force on the object. My hand goes away. But the object itself still has momentum, which means that when it runs into another object, it can apply a force to that object. So if we wanted to do the free body diagram of my blue car, when my red car, when it's staying by itself, it just is going to have, of course, gravity and normal force acting on it. I didn't draw those on there before because I was being a little lazy and short. But then the red car comes along, and that force is going to be applied to my blue car. So I draw it like this. So this force right here, this would be the force of my red car acting on my blue car. And that comes from the momentum. But that force is acting on a different object. It's not acting on the red car, which is why we don't draw it on the red car free body diagram. So I hope that that helps. If it's still a little cloudy for you, we can discuss it again when I get back to class. I just wanted you guys to have that before you go into today's lesson. All right, thanks.